My research project is about elastic and petrophysical properties variation within a mixed carbonate silicic deepwater fan of Wolfgang Formation Permian Delaware Basin. The data is located in the borderland of West Texas and New Mexico, and it is highly studied before by Kvali et al. 2020. Using the percentage of a clean gamma ray less than 55 API, they able to map the existence of deep water fan feeding to the Delaware Basin, and they be able to create something called the geometric of the fan itself that consists of axis, off-axis, lateral fringe, and the distal fringe. They make the idealist model of the facies succession vertically, that is so-called axis to off-axis, lateral fringe, and frontal fringe. Essentially, the center part is more dominated by more carbonate such as paraconglomerate and packstones, and then toward the lateral change to be waxstone and packstones, and in the frontal and the distal fringe they are dominated more the muddy materials such as mudstone. The facies change gradually parallel to the fan but change abruptly perpendicular to the fan. Their model is also validated by the core, and it is shown like in the picture in this picture that the low gamma ray and high resistivity commonly found in the axis to off axis consists of many carbonate material, rich carbonate material facies, whereas more on the distal and frontal fringe it is shown by high gamma ray and mildly or low resistivity, shown that is dominated by more muddy materials such as like mudstone. This project used 8 different wells that is located in the different part of the fan itself. This project using the technique of inversion base to know the mineral fraction by knowing the observed log. In this case, for example, by knowing the 5 different logs such as density, neutron porosity, gamma ray, and PEF, and resistivity, and by knowing each number of the density of the mineral itself, the neutron porosity, etc., we can know the mineral fraction of the formation. So this metric is known, we know this from the well logs, and we can know the volumetric fraction depth by depth. For example, when we decided to make the model of the rock physics using 5 different minerals and knowing the density, neutron porosity, and other logs, we can build the model. And knowing this and this matrix, we can solve depth by depth for the volumetric of the formation. After knowing the number of minerals that we want to make model of the formation and knowing the volumetric fraction of each mineral, we will try to calculate the effective bulk and shear modulus, which is in this case represented by K, SC, and mu SC. In this model, we use a simplified shape factor of sphere to make the model easier because also the lack of data that is available. The number of mineral is known from the previous calculation, and the bulk and shear moduli for each mineral is also known. After we finish the dry rock physics model, we then using the Gassman equation to substitute with the fluid that is contained in the subsurface so that we can mimicking the saturated fluid in the subsurface and make the accurate rock physics model. From this, we can deduce and we can estimate some important elastic properties such as Young modulus and Poisson ratio, which is a very good elastic properties that is typically used to decide the landing zone and fracturing for stimulation. We expect different vertical variation of mineralogy track that is calculated using the inversion-based technique before from the different response of logs such as DT and gamma rays as shown in this picture. After knowing the mineralogy depth by depth, we can compute something important parameters such as elastic properties, for example, Young modulus and Poisson ratio. Besides vertical variation of the petrophysical properties, we also expect variation spatially with respect to the position of the wells in the fans. Our anticipated result includes the well that is located in the middle because it is more dominated by more carbonate material tend to have the higher Phoebe and Vs, and then the bulk modulus and shear modulus, and also the Young modulus tend to be higher, the Poisson ratio tend to be lower than the well that is located in the distal and frontal fringe. This project is expected to have a number of limitations such as the inaccuracy in the rock physics model because in this case we use the well-logs data that is more on the lower set frequency of the lab, and the inclusion model is more accurate for the high frequency. The use of lead substitution by Gasmans is also violated a number of assumptions such as isotropic, homogeneous, and low frequency. The absence of ground truth resulting in an inaccurate in the model, the ground truth that is needed such as core measurement, XRE measurement, kilogram estimation, etc. The use of the simplified constituent constant in the inversion model to know the volumetric fraction of the mineral is also resulting in the unreliable result for the mineral estimation depth by depth. The implication of different phases in a mixed carbonate siliciclastic fan, we also expect different mineralogy that compose of different phases, and that translate to different response of elastic and physical properties of the rocks in different part of the fan itself.